Hello, and welcome to Agrosive Physics. Today is day 115, and what we're going to discuss today is resistance. Now, in any circuit, there are factors that slow down the electrons and hinder their motion. We call that electrical resistance. So, the definition is anything that hinders the flow of electrons. Now, with that being said, what happens when we have electrical resistance is a byproduct, and we call that basically heat. So when you have electricity flowing through a circuit, one of the things that you get is frictional heat. So that is a way that the friction manifests itself. What we have on wires is an insulator surrounding the metal of the wire itself. And that insulator's job is to protect the extra heat from getting out and getting into your walls. If you use the wrong diameter wire, different gauge wire than you should, you can produce a situation where an expected amount of electricity will flow, but the wire can't handle that much amperage. So what happens is you have overheating of that wire, and it could cause the insulation itself to melt, and ultimately the walls could catch on fire and you can burn your house down. So it's important to use the right gauge wire for the right circuit that you have. Now, as I said previously, a typical electrical circuit in your house is 15 or possibly 20 amps. Now, 15 amp circuits require 14 gauge wire typically. And it depends on the building code of the region that you're living in. But that will ensure, if you follow the proper code, that if you have anything less than 15 amps, it's not going to heat up enough to melt the wires and burn your house down. In the past, people used to have fuse boxes instead of circuit breakers. Now, if you have a fuse box in your house, that's fine. It still works perfectly well. But the fuses themselves happen to be about the same size as a penny. So people who ran out of fuses, instead of going to the hardware store and buying more fuses, would put a penny in between. Now, the pennies, older pennies, were made almost entirely of copper. At that point, the electricity would flow through, but the penny wouldn't melt at the same current rate. So people who put pennies in it would just constantly plug more things into the outlets and cause more current to flow through that circuit in their house. The penny didn't melt when it needed to, and many people actually burned their house down because of the fact that they didn't have the right fuse. A fuse is meant to melt at a certain flow of electricity, and a circuit is supposed to trip when it gets to the same electrical current flow. Now, resistance depends upon a number of things. It depends upon the nature of the material. Different materials are more resistant than others. We discussed previously about conductivity, and it's important to have highly conductive materials in order for electricity to flow. Now, resistors want to impede the flow of electrons. So many resistors that you may buy at the store are made of ceramics. They're plastic in some way, and that's going to really slow down the electron flow. They're not good conductors, so they're good resistors. And instead of calling it good resistors, we have a fancy term for the level of resistivity in a material, and it's called the resistivity. The other things that matter are the geometric shape of the material. Most wires are cylindrical, so they're circular if you cut them in a cross section, and they are cylindrical in their length. Now, in order to determine the ease at which electrons will flow, we look at the cross-sectional area. A bigger area will allow more electrons to flow than a thinner area. Now, the way gauge wires work is that the lower numbers mean thicker wires. So if you have a high gauge wire, for example, I have speaker wire that we're going to discuss later in the whiteboard example. It's 24 gauge. Now, that has a diameter of about 0.5 millimeters. Well, when you have that and you try to push electrons through it, it's going to be harder for the electrons to flow through that than a really thick wire. So a thin wire is going to have small cross-sectional area, and that's going to have high resistance. So the cross-sectional area is going to be indirectly related to the resistance itself. So the first two things are the the nature of the material, which is resistivity, and the geometry. And the geometry has two parts. It's the cross-sectional area of the cylinder and then the length. A longer length will be harder for the electrons to flow than a shorter length. So the longer the wire, the more resistance the wire has. The final piece of the puzzle is temperature. And if we think about it, as the electrons are flowing, everything in the metal, in the wire, is vibrating. The average kinetic energy, the temperature, is going to cause the molecules to vibrate. A higher temperature, more vibration. So the temperature is going to affect whether or not it's easy for the electrons to flow through the circuit. High temperature will cause the average kinetic energy to increase. More average kinetic energy means the molecules are vibrating more rapidly. And basically they're impeding the flow of electrons because the electrons keep bumping into the molecules. So a higher temperature results in more resistance. Now that's taken care of in our resistivity chart. In our reference table, we have a chart of resistance values for different materials. We have aluminum, we have copper, gold, nichrome, silver, and tungsten. And those values are listed in ohm meters. So it's how much resistance exists every meter of the material. Now copper is a common material that we'll use in wiring in houses. Gold is typical on high-end audio components because the connections with gold will allow the electrons to flow quite readily and increase the signal that's sent to the audio equipment. Nichrome is something that's used in a lot of toasters. You have nichrome ribbon, which which will heat up and actually be a positive byproduct because if you want to toast your food, you're going to want the resistance to cause heat. And then finally, tungsten is listed on the chart because many incandescent bulbs use tungsten filaments. So the tungsten is a common metal used in light bulbs. Now, if you look at the chart, one thing to note is that all the values are 10 to the negative 8. And they keep that consistent. So every one of the values will be times 10 to the negative 8. But nichrome has a much higher resistance value than the other. So when it's listed in the chart, it's actually listed as 150 times 10 to the negative 8 as opposed to 1.5. So watch out when you're using nichrome in a practice problem because the nichrome should have 150 as the base and then times 10 to the negative 8 as the secondary part. So watch out for nichrome. Every other material, for example, aluminum is 2.82 and copper is 1.72. Gold is 2.44 to the negative 8. Silver is 1.59 and tungsten is 5.60. So if you're just writing the values down quickly, it's a common mistake for students to put nichrome as 1.5 when the reality is it's 150. So watch out for that. Now, if we put these characteristics together, we end up with an equation for the resistance. And I call it the R equal PLA equation. So R equals rho, which is resistivity, times the length of the wire or the resistor that we're looking at, divided by the cross-sectional area. Now, the length is going to be in meters, and the cross-sectional area is going to be in meters squared. And cross-sectional area has one of two different major shapes. Typically, a wire is cylindrical, so the cross-section is going to be a circle, which is pi r squared. A lot of times we'll be given the diameter of the wire, so we're going to have to divide that by 2 before we do the pi r squared term. In other cases, it may be a rectangular shape, so what we're going to do is base times height. I'm going to do a practice problem in a little while where we look at the resistance of a gold bar. Now, in that case, we're going to have base times height instead of pi r squared because a gold bar is not cylindrical in shape, but it's rectangular. Now, with that said, these are all true if we have a constant temperature. On our reference table, the chart lists all the resistivities for our resistors based on a temperature of 20 degrees Celsius, which is room temperature. If the resistance or if the temperature goes up, the resistance values are going to go up because the resistivity changes. The length doesn't change, the cross-sectional area doesn't change, however, the resistivity of the material will change. Finally, when we're dealing with the resistors, we have a symbol that we use for resistance, and that's going to be an alternating jagged line that's up and down. It kind of looks like an EKG heartbeat. But what we deal with is a single up and down motion. The one I'm showing you with this slide has a number of up and downs. And what I've seen in some textbooks is they relate the value of the resistance to the number of oscillations of the up and down motion, almost a cyclical waveform. I typically stick to the single up down, and then I use the value of the resistor. I just write that value next to it. Now we have a number of different resistors. We have a standard resistor. We have variable resistors that can change. Those are typically potentiometers. If anybody has a dimmer switch in their house, as you turn the dimmer switch, that's going to adjust the total resistance, and that will change the voltage that's sent to the lamp. As the voltage changes, it will affect how much brightness the lamp exhibits, and we'll be able to see different values for the brightness based on the resistance. As the resistance goes up, the brightness will decrease. So using the R equal PLA equation will allow us to find the resistance of any material. Our values on our chart are based on the resistivities for metals. Typically the conductors we'll see in wires or things of that nature. But you could have resistivities of other values. For example, we could have resistance values for insulators as well. So it doesn't have to be a conductor, it could be a non-conductor. But at this point, let me take out the whiteboard and we'll look at a couple of sample example problems using R equal PLA. That's it for today. Thank you. Now, resistance in electricity is basically friction. It's a way of impeding or hindering current flow. When we use a symbol, we denote it with an up-down jagged line, almost like a heartbeat. And that represents the fact that it's difficult for the electrons to flow from this point to the next point. In fact, it has to go through this circuitous route in order to get here. So that is hindering the flow of electrons. And as they're drifting, they're going to bump into a whole lot of things during that process. Some textbooks will use more up and down motions to represent a bigger resistor versus a smaller one. I typically am in the camp of just do one, and then you write the value of the resistance underneath it, so then it all looks identical. So this may be 5 ohms, maybe this is 10 ohms, and they both look the same. I'm not going to draw more lines because we could have problems with resistances in the tens of thousands or even the millions. So it's going to be difficult to set a scale for how often I should go up and down with the resistor. So I typically stick to this method when I do that. Now we do have an equation for resistance, and I like to call it PLA because it looks like it spells PLA. R is resistance, and the unit is the omega. Rho, in this case, that's not a P, it's a rho, is resistivity. And it is a measure of ohm meters. L is the length, and that is measured in meters. And A is the cross-sectional area, which is meters squared. So, cross-sectional area typically will be a circle, because if we slice a wire, most wires are cylindrical. So if we slice that 9 times out of 10, it's going to be pi r squared. But that's not guaranteed. There could be problems with wires that are cylindrical in shape. That was not very good 3 dimensions, but it could be base times height, or it could be a square or something like that. Now, resistivity is based on the material. It is how resistant a material can be. So certain objects have higher values for resistivity. Some values are low. Metals are going to allow current to flow easily, so they'll have low resistivity, whereas insulators will have high resistivity. There's also another variable called conductivity, which is the opposite of that. So conductivity versus resistivity. So in that case, conductivity, a metal would have a high value and an insulator would have a low value. But in this equation, we use resistivity because we're trying to see how much impedance, how much the electrons are hindered during their flow. The resistivity is typically in a chart in the reference table, and we have a number of different values, anything from aluminum to copper to gold to nichrome to silver and tungsten. And those are typical values that are used because they're common in electrical wiring. Tungsten's common in electrical filaments in light bulbs. Copper wires are very common. Gold connections for audio equipment is top of the line, so you're going to use that when you're dealing with, trying to find audio equipment values for current flow or resistance or things like that. Now, the reason you have ohm meters here is because length is in meters and cross-sectional area is going to be in meters squared. So one of the meters will cancel here, and the other meter is on the resistivity. So it's the resistivity every, how many ohms per meter of length. Now, using this equation, we can calculate the resistance of any object, and we'll start with a practice problem or two and see if we can calculate the value. But basically, resistance is based on how long the wire is. Its cross-sectional area, a really thick wire, will have less resistance because there's more area for the electrons to flow through. And some metals will have tighter holds on their valence electrons, or some objects will have tighter holds, so it'll be naturally more resistant than others. So a good conductor will have low resistivity. And we can look at different types of problems that we can face. But if we remember the R equal Pla equation, that will set us up for finding the resistance of any object if we know what it's made of and its shape and how long it is. And that's our resistance.